Okay, welcome to the second video in the series about the distribution of the sample mean. So please open your notebook or your folder or wherever you are keeping the growing chart that we are developing as we work through all of this semester of statistics. This is about where we started with the number of observations in a population or a sample and the mean of a population or a sample. You should have many more symbols on that chart, and today we're going to add some more to them as well. So on your chart, you should have had the standard deviation for a population and a sample written as well. But let's talk about what we do about the sampling distributions and the symbols that we're going to use to talk about that. For a sampling distribution, to indicate the number of samples in the sampling distribution, we call that n sub x bar when we are talking about the sample mean. And right now that's what we're going to talk about. So let's add a little sample mean here to this column. Okay, so the number of samples that form the distribution of the sample mean or the sampling distribution is n sub x bar. Okay, the mean then is mu sub x bar, because we're going to use that sampling distribution to infer things about the population. The standard deviation of the sampling distribution of the sample mean is sigma sub x bar. However, because this is statistics, we can't just call that the standard deviation of the sampling distribution. We call it the standard error of the mean. Now, for the moment, we are going to be working with the case in which we know the population. We know the number of observations, we know the population mean, we know the standard deviation of that population. And we're going to see what would happen if we could take all possible samples of that population and what would be true about the mean of the sampling distribution, the standard deviation, or the standard error of the mean of the sampling distribution. And as you ran the simulations on that website, and as I ran them, we could see that the mean of the population was the same as the mean of the sampling distribution. However, if you remember, the standard deviation of the population did not equal the standard error of the mean. The standard error of the mean was less than the standard deviation. And in fact, there is a formula that you can use to calculate the standard error of the mean if you know the value of the standard deviation. So the standard error of the mean is equal to the standard deviation divided by the number n, the number in each of the samples that you took, from which you found the mean and then formed that sampling distribution. By observing all of these things, you were observing what is known as the central limit theorem. Regardless of the shape of the distribution, the sampling distribution of the mean becomes approximately normal as the sample size n increases. Here again is the URL for the sampling distribution demonstration that we accessed during the last video. You can go back there and convince yourself, if necessary, that the central limit theorem is true. You may do that by setting line 3 drop-downs to n equals 5 and the mean, and the row 4 drop-downs to n equals 25 and the mean. You will see that the distribution of the sample mean for the larger sample very quickly becomes normal. Remember, when you are playing with this website, that you are setting the population from which you are sampling. You are setting by changing the heights of those columns in the histogram. You're effectively setting the mean and the standard deviation of the population. You're sampling from that to get a distribution of the means of all of the samples that you've taken. Here's another chart for you. Notice that if the population is normal, regardless of the sample size, the shape of the distribution of the sample mean is normal. Center of the distribution of the sample mean, which should have a bar over the x there, mu sub x bar equals the mean of the population. The spread of the distribution of the standard error of the mean, which is in the last column, if we have a normally distributed population, it can be represented by that formula. And if the population is not normal, as the sample size n increases, the shape of the distribution of the sample mean becomes normal. Okay, and the center of the distribution, mu sub x bar, this is the center of the distribution of the sample mean, equals the mean of the population. And the spread of the distribution of the sample mean can be represented by that formula if we have a large enough sample size. In fact, to err on the side of caution, you should always use a sample size of at least 30. If you don't have a sample size of at least 30, you can't use that formula. It is not reliable. One final thought about a population. When we're talking about a population that is big enough that we want to take a sample from it rather than just learning the parameters of the entire population, we're not talking about small numbers. Now, if you are taking a random sample of this population, you don't want to duplicate the individuals. You want to have unique individuals in your sample. So to avoid duplication, we have also a rule of thumb about how the size of the population and the size of your sample should relate. And that rule is that the number in your sample should always be less than or equal to 5% of the number in your population. Or another way to say it, the number in your population has to be greater than or equal to 20 times the number in your sample. These are equivalent expressions. Take a look at some examples from your book. So for number 10, you are given a description of a population. You are given the mean equal to 64, the standard deviation of the population being equal to 18, the number in the sample, or the samples that you're going to be taking, is 36, okay, and we are being asked to determine u sub x bar, or the mean of the sampling distribution. What does that equal? And also, what does the standard error of the mean equal? So the first thing we have to ask ourselves is the sample size large enough for us to use the techniques we just talked about? Is it greater than 30? Yes, so we can move on from there. Now, since we have established that, and since we know the mean of the population, mu sub x bar just equals mu, and that's equal to 64. And the standard error of the mean, though, will be equal to the standard deviation divided by the square root of the number in our sample. So for this problem, the standard error of the mean will equal 18 divided by the square root of 36, which is equal to 18 over 6, which is equal to 3. So although the standard deviation of the population is 18, the standard error of the mean is only 3. So here would be the distribution of the population with mean of 64 and standard deviation of 18. Now, as you can see, it's kind of difficult to fit the sampling distribution of the sample mean on the same scale. It's much easier to see the standard deviations and such if we redraw it with its own distribution. But in truth, the only answers that were requested for this exercise were that the mean of the sampling distribution equals 64, and that the standard error of the mean equals 3. Let's take a look at number 16. For number 16, we're given a population, and we're going to be taking a sample size of 36. We know the mean of the population is 64, and the standard deviation of the population is 18. So we are asked to describe the sampling distribution of the mean. Okay? But that describe has a very distinct meaning, remember? We need to describe the shape. Well, they didn't tell us what the shape was. However, we're talking about describing the shape of the sampling distribution, and we have this information. N equals 36, which is greater than or equal to 30. And since that is true, we can say the shape is approximately normal. That is the first thing we need to do to describe the distribution of the sample mean, the sampling distribution of the mean. Either way you want to say that. Okay, so that's one of 3 things we need to describe it. Okay, the second thing is we need the mean of the sampling distribution of the sample mean. Well, the mean of the sampling distribution is just equal to the mean, which is 64 again. They like that 64. So mu sub x bar equals 64. That's the second thing you need. The third thing you need, okay, we have a shape, we have a measure of central tendency, and we need a measure of dispersion. So we need the standard error of the mean. And we know that that is equal to the standard deviation of the population divided by the square root of the number in our sample. So we just have to fill in the blanks. Standard deviation of the population is 18. The number in our sample is 36. And look at that. We have it once again. 18 divided by 6 equals 3. So the standard error of the mean equals 3. Should have pulled a different example. Okay, part B of this problem says, what is the probability that our sample mean is less than 62.6? Okay, so that's the question. Well, let's see. We know that the sampling mean is equal to the mean of the population, which is 64. And we should know that the standard error of the mean is equal to the standard deviation divided by the square root of the number in the sample. So again, we take the standard deviation of 18 and divide it by the square root of the number in the sample. So 18 divided by 6 equals 3. Standard error of the mean equals 3. Now we could graph this at this point. It would look like this. In fact, it would look just like what we graphed before, but we don't actually have to do that. Instead, we could calculate a z-score. The usual way we calculate a z-score is to find the z-score for the number in which we're interested. We subtract from that the mean and divide by the standard deviation. And that's the way we usually do it. Today, however, since we're doing the sampling distribution of the sample mean, the number we are interested in actually comes from up here in our problem. Okay, we are most interested in z equals 62.6. Actually, we're interested in those values lower than that, but that's the number we start working with. We subtract from that the mean of the sampling distribution, and we divide it by the standard error of the mean, which is 3. And that gives us a z-score of negative 0.466. Enough. Z equals negative 0.47. We are not done. We take that z-score to the z-table and find an area to the left of 0.3192, and that is the probability for which we are looking. Our time is up. I'll see you in the next video.